I'm sorry to say that the title of my talk is changed from the original one. And in my group, we are studying on the electronic and optoelectronic devices using carbon nanotube, graphene, metal, and polymer. So today, I'd like to talk about the single electron transistor using gold nanowires. So, single electron transistor is a transistor with one elemental charge transport owing to the carrier transport to the very small channel, which is called Coulomb island. In the system with capacitance of source, drain, and gate, the charging energy is very large, so the tunneling of electron into Coulomb island is prohibited. So in this device, the Coulomb oscillation, which shows very sharp periodical peaks as a function of gate voltage, and Coulomb diamond, in which the current suppressed and the number of electrons is fixed, observed. And this phenomenon is called classical Coulomb blockade, because this behavior can be explained by the classical physics. And these can be applied for the current standard logic circuit and qubit and so on. In contrast to the classical Coulomb blockade, there is a quantum Coulomb blockade, which exhibits in a system with large charging energy and large level spacing. In the system, single electron can be added to the discrete levels, and the total spin of S equals 0 or half can be controlled by gating, and the Zeeman splitting can be observed under magnetic field. And this quantum blockade is well studied in the field of fundamental physics, such as artificial atom, spin-dependent transport, spin qubit, and so on. And the SET is well studied by using various kinds of material. For example, lithographic metal iron is used in the early study of SET. And then SET with a gated two-dimensional semiconductor is developed by microfabrication technique. And recently, bottom-up nanowires, such as semiconductor nanowire and carbon nanotubes, are used as quantum dots, and very nice results, including quantum Coulomb blockade, is reported. So, one of the reasons why the nanowire-based SET is many local gates can be directly found on a single nanowire. And using this, we can add many functions to the SET. For example, by forming many local gates to one nanowire, coupled quantum dot, that is artificial molecules, is reported, or SET logic circuit, such as inverter, is reported, or local bandgap engineering is realized. So the local gating is a promising technique in the fundamental and applied physics, but reported materials for nanowire-based SET is limited to the semiconductor nanowire and carbon nanotube. So in this study, we fabricated a SET based on chemically sensitized metal nanowires. As a chemically sensitized metals for SET, only gold nanoparticles were reported. This is a result on the SET with gold nanoparticle, and very excellent Coulomb diamonds and discrete levels, and Zeeman splitting can be was reported, and recently the logic circuit with side gate is reported. However, the SET based on metal nanowire has not been reported so far. So in our study, we chemically synthesized gold nanowire using the technique reported here, and we fabricate SET with synthesized nanowires. So chemically synthesized gold nanowire is prepared by the wet process, where the gold chloride was reduced in a well-amine matrix at 85 or 35 degrees centigrade, according to this recipe. And we could obtain very thin and long gold nanowire with a diameter of 2 nanometer and length of from 1 to 100 micrometer. In this study, we fabricated two kinds of device. One is the bottom contact SET, where first we disperse gold nanowire on substrate, and then we deposit the electrodes. And the other is top contact SET, where first we deposit the electrodes and then disperse the nanowire on electrodes. Details will be talked later, but briefly, for bottom contact SET, the nanowire was fragmented and into very small pieces, and this device acts as a multiple quantum dot array, and the Coulomb blockade could be observed at room temperature. For top contact SET, this device acts as a single quantum dot, and strong gate control was realized, and the discrete level and Zeeman splitting could be observed from this device. So now for the bottom contact gold nanowire SET. So this is a fabricated bottom contact SET on the substrate with a landmark pattern. Gold nanowires dispersed, and then we deposit electrodes on the nanowire. I note that the measured gold nanowire was bundled with a number of 10 to 100. So this is the IV characteristic from 7 Kelvin to room temperature. This IV exhibits nonlinear behavior in the whole range of the temperature. In addition, this curve has very large threshold voltage of about 1 volt. So these results indicate this device, this transport is explained by the Coulomb blockade in quantum dot array. And in detail, the threshold voltage was decreased with increasing temperature. This is because the long pieces of nanowire cannot show the Coulomb blockade at high temperature due to small charging energy. In addition, we estimated the dimension of quantum dot array by using a power law fitting. Theoretically, the power law exponent of gamma is 1 for one-dimensional array, and gamma is 2 for two-dimensional array. From the fitting of this curve, we obtain the gamma equal nearly 1. So this indicates the electron percolates through nearly one-dimensional array. So this shows the transport model of bottom contact SET. In this device, gold nanowire bundle is fragmented and behaves as a nearly one-dimensional granular material. This fragmentation is due to the sample heating during device fabrication or exposure to the electron beam, as shown here. So, and unfortunately, this device acts as a multiple quantum dot, roughly in series. So this device has weak gate control of current, as shown the gate voltage dependence of current. So as a next step, we fabricated the top contact gold nanowire device. So, I will talk about the top contact gold nanowire device. So this is the fabricated top contact nanowire device. On the electrode, we dispersed nanowire, and nanowires formed between two electrodes. And this shows the IV characteristic in contrast to the result for bottom contact device. Ohmic conduction is obtained at the room temperature and 77 Kelvin. But at very low temperature of 0.23 Kelvin, we could obtain the Coulomb blockade. And this Coulomb blockade has a very small threshold voltage of about 5 millivolts. So this indicates this blockade is due to is from the single quantum dot. And this shows the gate voltage dependence of the current, and very clear and regular Coulomb oscillation is obtained, indicating the single electron transport in a single quantum dot. And this is a Coulomb diamond result, which is a grayscale plot of the current as a function of gate voltage and bias voltage. As shown here, very clear and regular Coulomb diamond is observed, indicating also indicating a single quantum dot transport. Red lines show the edge of the Coulomb diamond, and from the size and the slope of diamond, we could estimate the capacitances of source, drain, and gate. And using this capacitance, we can estimate the charging energy to be 12 milli-electron volt. And the conversion factor, which is efficiency of gate control, is estimated to be 0.13. This value will be discussed later. So I will show you the device model of this device. In our device, nanowire is on the nanowire is on the electrode, and this model can be we can use the model of a metallic cylinder on a metal plate. So in this system, we can obtain this formula, and in our device, gate capacitance can be given by this picture, including a silicon dioxide insulator of 500 nanometer. And the source and drain capacitance can be given by this picture, including a tunnel barrier of OLED amine with a thickness of 2 nanometer. Using this equation and experimentally obtained capacitance, we estimated the overlap nanowire length to electrodes like this. And this length are consistent with our device geometry. So this indicates that whole nanowire works as a single quantum dot. So I would like to show you about the advantage of gold nanowire SET compared with nanoparticle SET. This figure shows the result from gold nanoparticle SET. Very clear Coulomb diamond can be observed, but the conversion factor is very small, of 0.01. This is due to the screening of gate field by source and drain electrode. And it's very difficult to form a local gate electrode because the gap of electrode is very narrow, of a few nanometers. On the other hand, for gold nanowire SET, gate efficiency is very high, which is 10 times larger than nanoparticle. And it's easy to form a multi-local gate using conventional lithography because the gap of electrode is 100 nanometer. So this device is suited for the local gate control of transport or charge or spin. And finally, I would like to show you the two quantum effects in our device. One is discrete levels. As you can see here, in the parallel to the edge of the diamond, you can see a clear line here and here. This is a magnified one, and you can see the line here. This line is excited state from the discrete levels owing to the quantum confinement effect. And such excitation line can be also observed in carbon nanotube SET. So the gold nanowire is a high quality quantum dot comparable to the carbon nanotube quantum dot. And the other quantum effect is Zeeman splitting. This shows the magnetic field dependence of excitation spectrum measured along this dotted line. And blue one is the left side of Coulomb peak, and the red one the right side of Coulomb peak. And the magnetic field, Zeeman splitting is clearly observed. And from the Zeeman energy, we could estimate the Z factor to be 0.6. Generally, the G factor of free electron is 2. And in addition, it is reported that G factor of carbon nanotube quantum dot is also 2. So the obtained small G factor is indicates that there is a large spin orbital interaction in gold nanowire quantum dot. In summary, we fabricated two kinds of device, bottom contact and top contact device. And for bottom contact one, device behaves as a multiple 1D quantum dot array, and the Coulomb blockade can be observed at room temperature. For top contact SET, this device behaves as a single quantum dot, and strong gate control is realized, and discrete level and Zeeman splitting can be directly observed. And observed small G factor is due to large spin orbital interaction in gold nanowire. So the gold nanowire acts as a high quality nanowire quantum dot comparable to carbon nanotube. And as a future prospect, clear discrete level and Zeeman splitting can be applied for the device with spin state in a quantum dot, such as a qubit. And more interestingly, we could observe the large spin orbital interaction in gold nanowire SET. If we combine the single electron transport and the spintronics, it may be possible to realize, for example, single electron spin current or single electron Hall effect or inverse spin Hall effect, and so on. This study is supported by these collaborators. All experiments are carried out by two students in Keio University and EPFL Lausanne. And nanotube growth is supported by them in Tohoku University and Keio University. And electric measurement and theory is supported by them in NIMS and Gunma University. Thank you for your attention.